So here is the problem again. In the earlier series titled Judicious Guessing, we've been looking at the same problem. If this phi x, the right-hand side, only the function part, known function part, is made out of these elementary functions like this, we've been guessing, and as it's titled in here, let's think about the case we haven't really looked at in that earlier videos, is that what if this phi x is in the kernel of L? So if you stick this one in here and hoping that something, this one pops out and think about getting rid of the rest of the part, that was basically the strategy. But if you try phi x in there, if it is in the kernel, you will not get this one back. For example, if x to the second happened to be the kernel of this equation operator, then nothing will come out. If the cosine in e to the kx happen to be the kernel, nothing will come out. This will just disappear as you go through that. So here's an example, simplest example. We're not going to explore too much because the final answer to this one uses something called a variation of parameters. It's like this one here. So we will just use this as just a motivational example and enter the technique of this variation of a parameter as quickly as possible. But understanding this example is important to understand the setup of this technique. So we will look at an example. So example I had in mind is this one. Left-hand side is the order 2, second order equation with a constant coefficient. The right-hand side is the known function e to the x. That's our phi. And in this case, our operator L is d squared minus 2d plus I, and this factors the d minus I squared, or d minus I and a d minus I. That'll be a good form to play with. So if you factor it like this, you can see e to the x will, as you go through this first order part, it's going to be 0 and nothing will come out. So the question is what to do. What is it we're going to try? To some of you, what to try, maybe it's obvious, and to some of you not. So I'm going to pretend the letter, the case of the letter kind of people. So I'm going to look at the solution of the kernel and learn from there. So here I'm going to write down the kernel of L. We know is made out of first kind, which is e to the x, but it has degree 2, order 2, therefore there's another one, C2, e to the x, and we know it comes from multiplying x there. So let me explain it this way. The first, when you go through d minus I, that's the first operator we go through, and then the second operator we go through on the left is d minus I. Whatever is killed or annihilated here is e to the x, and whatever they go through and dies it again, something has to survive so that we have a pickup dimensional 2 is going to be whatever it dies in here is going to be another e to the x in here. So let me explain this part again. The way we understand this kernel is e to the x, that part, if you go through the first operator, it dies. But there's another part, there's a factor in here. After you go through this part will die. That's what this exactly says. But something will survive when you go through the second part of the operator, and then it dies there. So what dies in the second operator, first order operator, everything that dies here is made out of this e to the x. So whatever that survived out of this d minus I and dies it here must be e to the x that came out of there. So x times e to the x was actually the function if you stick it in there, and survives and becomes e to the x. When you go through the second factor, it eventually dies. That's what really happened. So let me pull it up a diagram. So I sketch it like that. There are two functions to try. E to the x is inside our kernel, and x times e to the x is another function inside our kernel. If e to the x goes through this d minus I, this goes right into the 0. This dies through this d minus I. That's what this is. But when this one goes through, it doesn't die. It survives and becomes e to the x. And of course, whatever goes through in here and becomes 0, let me put the 0, another copy of 0 in here, that must be e to the x. So it guarantees that. And after this part goes through, because it's in the kernel, after you go through d minus I, it's going to be a constant multiple of e to the x, so that it went through. Second time, it becomes a 0. So that's the lesson from some of the answer we already know. So we've been talking about this x times e to the x and x times e to the x, and let's see what's going to happen if you try this one. Now I think I misspoke, and this one will survive with this d minus I, so let me summarize it here like this, after I erase it. So if you go through this d minus I, which is not our operator to solve it in here, with this x times e to the x, it's probably constant times e to the x. That's our conclusion. So let's actually calculate it. If you differentiate one time, the whole thing, it's a product rule. It's e to the x plus x times e to the x minus, if you don't differentiate it, it's x times e to the x. It's obviously all e to the x. So here's an idea. And if you're looking at an operator and the phi function is the kernel of this operator, you're not going to try e to the x. Maybe you're going to try x times e to the x. So when you differentiate, and this piece, the phi x you want, kind of survives. So that's the lesson from looking at what happens inside the kernel in here. So let's think about this problem again. So we know, but if you try e to the x, it's going to be 0, and even x times e to the x, because that's still the kernel of this operator, it's still going to be 0. So we're not going to try neither of those, but next thing we may try to, from that experience, by analyzing what happens to x times e to the x and one of the factor in there, let's think about what to try. Is that if you try the next level, of course, x squared e to the x in here, if you differentiate 2 times, and think about that, the product rule for a 2-time product rule, and if you differentiate this one 2 times, e to the x definitely survives. So, and this one will pick up e to the x, and the rest of the pot may mess up, but since definitely it's not going to be 0. So there's a good chance maybe you get something out of it. So this is what we wanted to try. So let's differentiate it 2 times, use the rule. So differentiate it 2 times to 2 to the e to the x, and 2 times 1 time we'll get 2x, and 1 time is e to the x. And if you differentiate this one 2 times, you have just nothing in there, e to the x. So that's the second derivative part, and the first derivative part is -2, and then y prime will be here 2x e to the x plus x squared e to the x. That's this part, and plus y itself is x squared e to the x. Okay? Let's see what happened. If something interesting happened, and understanding that part is going to be the main goal of this part of the video. So let's collect e to the x here. E to the x, we have coefficient 2 from there. That's not e to the x, and that's it. That's the only coefficient for 2 times e to the x. Let's look at x times e to the x. This time the coefficient is 4 there. That's another x times e to the x, is -4. And there's no more x times e to the x, so that's 0. That's good. We didn't want that x times e to the x. Let's look at x squared part. We have x squared here, that's 1. And there's a -2x squared, -2, and here's a positive 1. And accidentally that became 0, so it just gave you this 2 times e to the x, and there's this accidental canceling what's going on right here. That's kind of strange, but if we're, by sheer luck, we have this 2 times e to the x. So if you divide that constant multiple, so we found an answer. Half times x squared e to the x is going to be e to the x. So we found a particular solution of this equation by just trying this one. And this part needs to be explained. If you look at more and more examples of this type, you will see this is happening. Some parts are cancelled out all the time, so it gives you this convenient answer like this. So we need to look into what's really happening in here, and that'll lead us to the method of a variation of. So at this time, let me use a lot simpler example to motivate the method of variation of parameters. So this is a bits and pieces of what we've been just discussing. So if you look at it here, how we're going to get this e to the 2x, from that example, the idea is that if I stick an x here, that'll probably survive in here, and we'll something do about it. We can do something about it. So here, the idea is that, okay, try, from that early example, x times e to the 2x, because we know e to the 2x is a kernel of this factor. If it is 3x, you know it's going to survive. So that will be a lot easier case. But in that case, if you differentiate 1 times e to the 2x and plus 2 times x times e to the 2x is this y prime part, negative 2 times x times e to the 2x. So that's, you can see this cancel out. This part disappears for us. And e to the 2x there. So here, again, you see some sort of cancellation that things turn out in our way. So exactly what we wanted. So we found that example in here. So let me explain this first order case in a more functorial way, more general description. Here is the explanation of this cancellation part. Suppose we have L, which is slightly more general, but still first order. So d minus this time is a px, and I in here, that's the operator. Then the kernel, let me change that to negative. Then where our kernel is, you know, is antiderivative e to the px there, right? So since that's the kernel of this one, if you stick it in there, it's going to be 0. So what we're going to try is x times e to the px. Let's see what happened. If you differentiate it, e to the px survives. Capital P, x times e to the px. Differentiate, I forgot to differentiate this part, so I'm going to multiply little px there. Minus px times e to the px. Here, this x and x, I forgot to keep that x in there. X is in there. So if you factor out x, what happens is that x times, this is the derivative of e to the px. So that's the derivative of, so I can write it as a derivative like this, e to the px instead of e to the px times px, and minus, this is the px times x times e to the px. Parenthesis. This x is factored out, so we have only this part in here. So we can rewrite e to the px in there, and plus x times, if you look at here, the argument for the both operators e to the px, and here's e to the px multiplied, so we can write it as a d minus px I of e to the px as an operator, bracket. So because that was the kernel of that part, and is obviously 0. So this is a little bit more general description. If you description of why there's these things that cancel out. If you bump up the order of the operator, a little bit more complicated thing is going on, but we wish all this thing disappears and this part becomes just what we want, and that's the basic motivation of the variation of a parameter. Something like this original operator form shows up, and a little variation, and then we want to make all the variations of this part 0. So let me explain it this way. In just first order case, it was simple enough. What happened is that this one really appeared in there as a derivative form, and what happened to that part is x was kept there, and this one, and x is not differentiated as if x is kind of factored out. L is only operating on this e to the px part. That seems like what it happened, and we want to kind of generalize this for the first case into something interesting happens. So let me start with L of whatever, it's not x, but something else, and still multiply e to the px, and something like this happens. Right, here is the form, and they usually use this letter V, so instead of X in there, I stick it in the V. It seems like after you're going through the product rule, something nice happens. So this one is differentiated, V prime e to the px, and V and e to the px, little px, that is the second derivative part, and negative px times the function V and e to the px. As you can see in the second part of the V is untouched, is not differentiated, is a part of what product rule does. So if you group that part with this px factored out, and with V is out, and this, sorry about that, also P is out. P is not out, it's just a derivative. It's the same as derivative of a little p xi with e to the px applied. So this part is a derivative of e to the px, and this part is a px times e to the px, but v is common and is factored out. So no matter what the v is, this part will be 0. It only leaves this v prime e to the px. It's a nice part not only for x. If you stick anything in front of e to the px, what's going to happen is that e to the px just pop out as if this is untouched, and v is just differentiated. So let me go over here and change the problem a little bit. If L is the same as this one, if you're looking for a function y such that this is like a sine x, and we don't even know what that px is, all we know is just some function in front of px, then you can go through integral method because it's first order, it's as simple as that. But let's use this idea. Something very interesting happened if you use this idea. If you just try, not knowing what this v is, just try this e to the px kernel, multiply by the sum function, and since it's not constant usually, this is not going to be 0, something will pop out, and we just looked at it here, e to the px, which is the antiderivative of little px, and that's what happened. And all we want to know to figure out the v, because this p part's known, such that this one becomes a sine x. And if you can figure out v that does it, and that's going to be a particular solution. And here, v prime, there's no other v's appearing here, nicely isolated. Of course, v prime is going to be e to the negative capital px and sine x, and v can be just an antiderivative, any antiderivative of e to the negative p sine x dx, which is multiplied to this function in here. So that's a very shortcut of integration method, the answer you can get out of the integration method. So this is the simplest example that shows everything about variation of a parameter of a degree 1, order 1.